Hey guys, so in this problem, we are asked to evaluate an integral using Theorem 4, the Riemann sum method. Same thing. So I just want to point out that a lot of students, whenever they see an integral, they automatically go to this process and just go straight for it. But the thing is that this process is really annoying and really difficult, as I'm sure you all know. So we don't want to do this right off the bat unless we're told to in the problem. If it says use Theorem 4 or evaluate using the Riemann sum method, that's when you do this. Otherwise, just use the fundamental theorem of calculus part 2 because it's a lot simpler and we can actually use it later in the problem to verify our answer because it's easy to get lost in this process. So we can use it to make sure we did all the steps correctly, which I highly recommend you do as well. So we are given the theorem in the test. You don't have to worry about memorizing that. She will give that to you. And on the right side, I have some of the sum properties we're going to end up using. You will not be given that in the test, so do memorize those, and I just have that for reference for later in the problem. So let's get into it. The first step is going to be identifying the components of the left side of the equation, which basically just means looking at our integral given and finding our a, which is a 1 in this case, our b, which is 6, and f of x, which is x squared minus 4x plus 9. All right, so there you go, components of the left side found. The harder part, slightly harder part, is finding the components of the right side, because we want to be able to use that right side to evaluate our integral, right? So we have to find delta x and x sub I so we can find f of x sub I. So let's go ahead and tackle that first part, which is finding delta x. So delta x is going to be b minus a over n. And in this case, that means 6 for b, a for 1, and over n. We have to let n sit there, because remember, we're going to let that approach infinity later in the problem. So we're just going to let that chill for a little bit. And that is 5 over n. So there is our delta x. So now we can use that to find the other component of our sum expression, x sub I. And x sub I, of course, is a plus I times delta x, where a is 1, and we just established that our delta x is 5 over n. And we multiply that times I. So x sub I is 1 plus 5i over n. And there we go. Now we can go ahead and use x sub I to find f of x sub I. And of course, you could just combine these two steps. I just like to have them separated, personal preference. And of course, f of x sub I is just f of 1 plus 5i over n. So wherever we see an x in our f of x expression, we replace that with 1 plus 5i over n. And so when we do that, we get 1 plus 5i over n squared minus 4 times 1 plus 5i over n. And plus 9 is just going to be in the back there. And of course, we have to do some simplifying. And so when we do that, for this first part, we get 1 squared plus 10i over n plus 25i squared over n squared. And when we distribute this negative 4 into the parentheses, we get negative 4 minus 20i over n. And the 9 did absolutely nothing. It's just sitting in the back there. Okay, and so when we rearrange a little bit, simplify, combine some like terms, we're going to end up with 25i squared over n squared minus 10i over n, and 1 minus 4 plus 9 gives us positive 6. Cool. So now we have identified all the components of the right side of our equation in Theorem 4. And so we can write that equation out. And that's what we're going to do. So write our sum expression. Cool. Using the components that we just found. And to do that, I'm going to need a lot more room. So I'm going to go ahead and erase some of this stuff. If you need to copy some more, go ahead and just pause and do that. But let me just clear up some room real quick, and there we go. So we have now established that the integral from a well, okay, the integral in this case from 1 to 6 of x squared minus 4x plus 9 dx is equal to the limit as n approaches infinity of the sum as I goes from 1 to n of fx of I, which we just found. So I'm just going to plug that in there. We got 25i squared over n squared minus 10i over n, and then plus 6, and times delta x, which we found as 5 over n. Okay. So now we just need to simplify this expression on the right here, and then we can apply some sums and let n approach infinity, and at that point we will have evaluated the integral because we said the two are equal. So then after that we'll be done with the problem. So let's do that. After some simplifying, of course. So we get limit as n approaches infinity of the sum. Let me rewrite that sum because that looks really messy. The sum as I goes from 1 to n, and it's going to involve what we distribute from that 5n. So we get 125 I squared over n cubed, which is distributing that 5n into here, minus 50i over n squared, and then 6 times 5 over n is just going to give us 30 over n. And of course, as we know, we can split this sum up into the different terms. So I'm going to go ahead and do that. And we also know that we can bring everything besides the i's out of the sum, out of like the little sum expression. So I'm going to do that as well. So I have 125 over n cubed times the sum as I goes from 1 to n. And I squared is left in there. Okay, because the I is really all it cares about anyways. And then I'm going to write 50 over n squared times the sum as I goes from 1 to n of just I, and then plus 30 over n, and then what's left over in there is just the 1. So of course there's different ways of splitting that up, slightly different ways, but we always end up with the same thing. So let's go ahead and substitute now, because now we can clearly see that this guy here is equal to this guy up here, right? So we can just substitute that and the I and the 1 into what our sum properties tell us they're equal to. So we have to leave this limit as n approaches infinity here still though, of course. So, and that guy does not change at all, the 125 over n cubed. But this guy changes to n times n plus 1 times 2n plus 1. So now what we're doing is we're getting rid of all these little sum expressions, these weird little notation things, so that we can deal with the limit only. So, and the sum of I is n times n plus 1 over 2 plus 30 over n, and the sum of 1 is just going to be 1 times n, right? Because the sum of a constant is just that constant times n. So the constant here is 1, so it's just n. And now we can simplify a little bit more. We can cancel out this n with the n down here and make that squared. This n gets canceled, this becomes n to the power 1, and these two n's cancel all together. So what I'm going to do now is write our limit, because we haven't evaluated that yet. And I'm going to bring the 6 out of there and just leave the n's by themselves. So we have n plus 1 left over and 2n plus 1 as well. And the n squared can be brought under there. Okay? And the 50 over 2, that's like an 8. The 50 over 2 times n plus 1 over n, and of course the n's were canceled and we have 30 left over at the very end there. Okay, so at this point we simplified our sum expression We evaluated the sum, so those are gone. Now all we have to do left is evaluate the limit, and then we will be done. So let me go ahead and erase the stuff up here so we have some more room so we can finish the problem. There we go. I'm going to bring this guy up here. Okay. So this is going to involve a little bit of simplification again, right? And distributing and whatnot. So we're going to have the limit, which we have not evaluated yet, 125 over 6, and foiling that little expression out is going to give us 2n squared plus 3n plus 1 over n squared. And this 50 over 2, of course, simplifies to just 25 times n plus 1 over n. And there's nothing to simplify over here, that's just 30. Okay, so hopefully at this point, we've become pretty comfortable with evaluating limits, infinite limits like this. And so of course we're just going to divide, in order to evaluate this, we're going to divide all the terms here by the highest power of n in the denominator. And so what we're going to do is 2n squared over n squared plus 3n over n squared plus 1 over n squared, right? Over n squared over n squared. This is just about evaluating this limit. And so in this particular case, this quotient is n over n plus 1 over n over n over n. And this 30 at the end here, we don't really have to do anything with that because it's just a constant, right? So that's not going to change no matter what we do. So that's just going to stay 30. Okay. And now we know that these n's cancel here, and this n's going to cancel. We're going to leave an n in the denominator, and that's just going to stay as 1 over n squared. This becomes 1. This becomes 1. And then this becomes 1 as well, and the 30 does not change. So now we can apply the limit, right? And when we apply the limit, there's nothing to apply for this expression because it just became 1. This guy goes to 0. It's a number over a very large number, so that's just 0. This guy also goes to 0, 1 over a large number, 0. This guy is 1. This guy becomes 0. That's 1, and the 30 has not changed. So, our expression after evaluating the limit is 125 over 6, and remember, the 2 stays there, over 1, minus 25 times 1 over 1, plus 30. Alright? So, we get 125 over 3 minus let's just put plus 5, okay, and simplifying that a little bit, we get 125 plus 15 over 3, which is 140 over 3. And that is our answer to the integral in the very beginning. It was that long process of converting it into a sum expression, evaluating the sums, and applying the limits. So let me just save this answer for us here, and we are going to check our answer using the fundamental theorem of calculus part 2. So I'm going to go ahead and once again get some more room for that whole process. Here we go. Okay, so we know that the fundamental theorem of calculus tells us that this integral here, 1 to 6 of x squared minus 4x plus 9 dx, is equal to the derivative, if this is f of x, or the antiderivative, sorry, evaluated at 6 minus the antiderivative evaluated at 1. Okay, so we know that the antiderivative is x cubed over 3 minus 2x squared, right? The 2 cancels and the 4 becomes 2, plus 9x evaluated from 1 to 6. Okay, so when we plug in 6, we get 216 over 3 minus 2 times 36, which is 72, plus 54, minus when it's evaluated at 1, we get 1/3, minus 2 plus 9. Okay, so simplifying some more, we get 216 over 3 minus, that becomes 18, minus 1/3. That is 7 in there, it's going to become minus 7. And this equals 216, or 215, let's just combine some like terms here, over 3 minus 25. Okay, so it looks a little bit different, but I think we'll find that is actually the same. So we know that this is 215 over 3 minus, it's going to be 75 over 3, and that ends up being exactly 140 over 3. So we have confirmed that the integral from 1 to 6 of x squared minus 4x plus 9 dx equals 140 over 3.